Good day, everyone. We are Modula and Podrick.
Let's dig into what is going on in tech and science news.
All right, today we're jumping into a thought experiment that pushes engineering, physics, and even our sense of who we are right to the absolute limit. It's a huge question, maybe one of the biggest we could ask. Could we actually move the Earth?
So picture this. In about 1 billion years, our sun is going to get hotter and brighter. So much brighter, in fact, that it will literally boil away Earth's oceans, and our home will become totally uninhabitable. So some future version of us faces a massive choice. Do they leave Earth behind, or do they try to move it? What if we could physically nudge our entire planet's orbit outward, to the cooler, safer neighborhood where Mars is hanging out right now?
Okay, so obviously this isn't something we need to worry about tomorrow, but it's a fascinating long-term puzzle. The sun getting hotter is a slow but totally relentless process. So let's start by looking at the incredible engineering challenge this would be, planning a planetary move with a deadline of 1 billion years.
Now, to even think about moving a planet, we got to talk about energy. You see, a planet's orbit isn't just a path it follows. It's actually a very specific energy state, a delicate balance between its forward momentum, that's its kinetic energy, and the constant pull of the sun's gravity, its potential energy. So moving Earth isn't like we can just give it one giant shove. It's about slowly, methodically adding energy to its orbit over a huge amount of time to lift it further away from the sun.
So what's the actual cost? I'm talking about the energy bill for moving an entire planet. The laws of physics are pretty clear on this. You want to change an orbit, you have to pay up. So let's break down the numbers because they're kind of wild in a couple of different ways. Let's start with a number that's going to sound weirdly small. If you could perfectly and continuously apply a force to Earth for that entire billion-year period, you'd only need about 850 horsepower. That's it. That is less than what you'd get from a single high-end supercar. So what's the catch? Well, the catch is the huge difference between power, how much energy you're using at any one moment, and the total energy you use over time. And while the power is small, the total energy you'd have to pump into the system over 1 billion years is absolutely colossal. We are talking 3.8 times 10 to the 31st joules. That's a 3.8 with 31 zeros after it. And since a number that big is basically impossible to wrap your head around, let's put it into perspective. Okay, let's really put that number into context. On this chart, that first big bar, that's the energy we need. Now look at the second bar. That's the sun's entire output for a single day. They're almost the same. And then look way over on the right. See that tiny little sliver? That's all of humanity's electricity generation for a whole year. We would need about 500 billion years of our current global power output to make this move happen. The scale is it's astronomical.
But okay, let's just pretend we could somehow get all that energy. The problems are just getting started. You see, moving the Earth isn't something that happens in a vacuum. It would send massive ripples through the whole solar system with consequences that we can barely begin to predict. You know, we have this image of the solar system as this perfect, predictable clockwork machine, right? Everything in its neat little orbit. But the truth, it's way more chaotic. The planets are all locked in this incredibly delicate gravitational dance. And even the tiniest little change today can snowball into massive, completely unpredictable effects millions of years down the line.
Just how sensitive is it? Well, check out this quote from astronomer Jacques Lascar. An error in knowing where Earth is right now of just 15 meters, that's about the length of a city bus, makes it impossible to predict where our planet will be in 100 million years. Think about that. So can you even imagine what would happen if we intentionally moved our planet by tens of millions of kilometers? We could accidentally kick Mercury into the sun or send Mars flying right at us. And this isn't just some abstract theory. We can see these little interactions happening right now. Geologists have found evidence of a 2.4 million year cycle deep in our oceans, and it lines up perfectly with tiny gravitational nudges from Mars. Mars's little bit of gravity already affects our planet's climate over these vast timescales. If we deliberately moved Earth, we'd turn those gentle nudges into catastrophic shoves. All right, so if moving the Earth is just way too risky, what's the other option? What about Plan B? Why not just pack our bags and move to Mars? I mean, it's already in the right neighborhood, right? Well, the biggest issue is that Mars is not exactly move-in ready. First off, the gravity is super low, only about 38% of what we're used to, and that's a huge problem because it means the planet just can't hold on to a thick atmosphere.
And to make things worse, it doesn't have a global magnetic field like Earth does to protect it. So for billions of years, the solar wind has just been blasting its atmosphere away into space, leaving it cold, dry, and blasted with radiation. So the big question is, could we fix it? Could we actually engineer a new home for ourselves? This idea has a name, and you've probably heard it. It's called terraforming, rebuilding an entire planet's environment to make it more like our own. But this opens up a whole new set of really profound questions.
This is where things get really complicated, and not just technically. It becomes an ethical question. And honestly, Carl Sagan put it better than anyone ever has. He said, "If there's life on Mars, I believe we should do nothing with Mars. Mars then belongs to the Martians, even if the Martians are only microbes."
And that's the core of the dilemma, isn't it? The whole point of terraforming is to make Mars livable for us. But the very things we would do, creating an oxygen atmosphere, adding liquid water, bringing our own microbes, would be completely poisonous to any native Martian life that might be there, adapted to its current environment. We would risk committing an accidental interplanetary genocide before we even knew we had victims. And this just opens up a whole other can of worms. Beyond the ethics of it all, there's a simple question: who gets to decide? A project this big isn't just a science project. It's a massive geopolitical puzzle. How could all of humanity possibly agree on the fate of an entire planet? Our only real starting point is the Outer Space Treaty from back in 1967, and it lays out some basic ground rules. For one, anything we do in space has to benefit everyone. 2, no country can just plant a flag and claim a planet. 3, we have to avoid contaminating other worlds. And 4, governments are responsible for what their people do up there. But could a treaty from the 60s really handle something as huge as terraforming? And this is where we get into this really fascinating new idea called planetary geopolitics. It's all about figuring out how these massive, world-changing technologies force us to invent totally new ways of making decisions together. I mean, we're not talking about managing a country anymore, or even a continent. We're talking about managing the destiny of an entire world. So in the end, this whole wild thought experiment, whether it's moving Earth or remaking Mars, it really just forces us to look at ourselves. As our power to change things grows, so does our responsibility. And the final question isn't really about the physics or the engineering, is it? It's about our values. What's more important? Our own survival, no matter the cost, or respecting something new, something unknown? That's a choice that won't just define what we can do, but who we are.